Okay, so good evening and welcome to this PMRF doubt clearing session on real-time digital signal processing. I am Shouharda Ghosh, a first-year PhD student in Electrical Engineering Department at IIT Gandhinagar. This is week 11 and it covers image processing applications, and we shall mostly be talking about JPEG and DCT. Okay, so the main focus of today's talk is on image compression. So we will first introduce the notion of why we require this image processing, image compression requirement. Why do we need this? So we'll realize that just as in the previous week's discussion about speech, we will also talk about compressing techniques and reducing the bit rate. So here also we will try to see how and why we require this same compressing techniques in images as well as same holds for videos as well. Okay, so let's start with a simple example. Okay, so we first consider a black and white image and which has a resolution of 1000 pixels cross 1000 pixels both in the length and width, and each pixel is 8-bit, uses 8-bit to represent the intensity. So if it's 8-bit, so what is the range? And you understand that in images we actually use unsigned integers, so it will range from 0 to what's 2 to the power 8, that's 64 into 4, so it's 2 to the power 8 minus 1, that's 255. So we'll have a range as a matrix of 1000 cross 1000 with entries ranging from 0 to 255, where 0 corresponds to completely black, okay, completely black pixel, and a 1 corresponds to a completely white pixel, okay, the intensity. And if I so if you click on the sliders, you can see over here RGB, here RGB all range from 0 to 255. so if I put all of them white, so we will be talking about the colors later, okay, but still I'm showing this for a reason that the pixel values range from 0 to 255, okay. So that's fine. So each pixel occupies 0 to 2 from 0 to 255, 8 bits each. So the total space required or number of bits required is how much? 1000 into 1000 into 8. So it's almost 8 times 10 to the power, how many zeros are there? 6 bits. So you can write 8 megabits or 1 megabyte, because 1 byte is equal to 8-bit. So a single 1000 cross 1000 pixel image requires almost that way black and white requires 1 MB. Now let us assume that it is a part of video sequence with 30 fps, frames per second. So the total size of a 3-second video is how much? It's 1 MB for a single image, and then in 1 second you have 30 images, and we have 3 seconds. So how much does it turn out to be? Turns out to be 90 megabytes, or 7.2 times 10 to the power 8 bits. Okay, so you can very well understand that if you have to transmit 90 megabits per second, how much bandwidth it is taking. Okay, so you require very high bandwidth systems and a big so you understand that the lot of requirement of data is required. So what happens is that in reality the images are quite redundant in nature. So we will see later what that means, but let's say briefly. For example, if you are seeing the screen, okay, so if you see my white screen over here where I'm writing, so most of it is white, only a certain portion, a certain percentage of it is kind of these letters are visible, the purple color. So if I transmit it as it is, then it will take a huge amount of data. But then if I take advantage of the fact that data is actually sparse, because it's not changing every time. You can see in the spatial domain the there's not much change in data, only at some spaces. So I can make use of this sparsity and try to compress this data. So for compressing, we have a standard called the JPEG, which is called the joint photographic experts group. Fine. So in JPEG compression, we will learn about DCT, image quantization. So hello Jagannath, am I audible? Please let me
Yes.
know. Okay, so Jagannath, till now actually I've just started. So basically this week covers the last module, because the week 12 will just have the lab experiments, and that is not of much concern in these problem solving sessions. So this is the last theory session that we'll be having. So we are talking about image processing applications, and we'll be focusing on JPEG and DCT. So basically I told that let's suppose we have a black and white image which is 1000 pixel cross 1000 pixel. So each pixel is represented with 8 bits. So in image actually represented using unsigned integers, and when you have 8 bits, so you represent it from 0 to 255. And for example, I showed over here my pen color. So over here, if I choose the slider, you see this red color slider, I can change it from 0 to 255. Okay, so each of these I'll talk about colorful colored images later, but even in the single slider also you can see it ranges from 0 to 255. So it's a pretty standard thing. So this image of 1000 cross 1000 pixel, which is a megapixel image, so how much space is required? So you see that you require almost 1 megabyte space. And let's suppose this black and white image is a part of a video, okay, and the video the standard video transmission rate is 30 frames per second. You see 30 frames in a single second. So for such a 3-second video, you have how much space? That's 90 megabytes. Okay, so you understand that a small video of 3 seconds occupies so much of space. So when you transmit this, how much bandwidth would be required, right? It is immense. And let's work out together. We're talking about, like, even if you talk on 80s 90s, even during those times, think about such high data rates. You can't think about them. But the biggest advantage is that the images or the videos have a good deal of redundancy. And what is that redundancy? We'll talk about that later. So using the redundancy, you can actually compress these images, and one such compression algorithm is JPEG. It's a standard rather. So and an important thing is that this is a lossy compression. Okay, that means that you are losing out some data. Okay, so in digital communication you must have learnt about lossless methods. Let me write that down. So lossless methods such as Huffman encoding, arithmetic coding, Lempel Ziv, LZW, which uses a dictionary and that kind of thing. So these lossless methods are actually inefficient for video and obviously images. Okay, so what JPEG does is that it uses transform coding. Okay, and it is based. And what does transform mean? We have learnt about various transforms, C transform, Fourier transform. So in image domain we use the image domain transform and then code the transform, the spatial the frequency domain transform. And why do we do that? Because majority of the let me not write these things anymore, let me just narrate it. So a large majority of the image content that you can see are relatively constant. For example, if you see the screen over here, let me use a laser pointer. So if you see this small region, so you will be able to see that it's completely white, right? So it's completely white. Only certain regions over here you have some change, some letters, some changes in color. Okay, but even in these regions, even in between these layers, there's still white space, right? So if you try to see the matrix of image pixels, okay, so the entire data will be filled into a matrix, will be filled with zeros, and only a few regions will be filled with non-zero integers. Okay, so you can say the variation is quite less. So when variation is quite less, we call that a low frequency signal. Just as in audio or in Fourier transform we learned about low frequency and high frequencies, similarly in images, when we have very few for example in images, how would we see the frequency content? So for example, in this image, what is happening? It's white over here, but suddenly you have a black. Okay, so there's a sudden change in the intensity color, and then again it's white. So if I try to say what is this frequency content like, so you will be able to see that here it's low frequency, there's no change, and suddenly there's a high frequency over here and again low frequency. Understood? So this is what I talk about frequency in the spatial domain. So now most of the almost all the real life images, the frequency content is actually very low. Okay, high frequency or very high changes are quite less. So it is very unusual for the pixel values nearby to keep on changing very fast alternately. And that too, we talk whenever we talk about image, we don't talk about image as a whole, we partition them into various subblocks, and one such subblock is 8 cross 8 pixel wide. Okay, so once you transform it into frequency domain, what you observe that most of your energy is concentrated in the lower frequencies, and high frequencies have almost no component, almost zero. So if you try to get rid of this useless or the not required, not so important high frequency components, then that would be really good. Okay, and experiments have also suggested that for human beings we are much less prone to errors in the high frequency domain. Okay, so if there are changes in the high frequency spatial domain and we remove them, then our eyes won't be able to look at that. Okay, so let us look at JPEG coding. What are the steps involved? So we am talking about colored image now, and a color image can be represented in the three planes RGB, means red plane. Let me use color. Okay, so there's a plane of red, there's a plane of green, and there's a plane of blue. Okay, so and each of these, and if you look at each of these planes individually, okay, if you take out R, if you take out G, or if you take out B individually, they are black and white images on their own. Okay, it's only when you combine them and there's some kind of a interpretation. Okay, it's not that when you add them together you get some kind of a color. It's the visual system. Okay, it's the monitor of the display, it's the LEDs that blink up which create this color. So depending on the intensity, that will be the intensity of the LED that will glow up, and you have one matrix of LEDs for red, another matrix for the green, another matrix for the blue, and based on the pixel intensity values, that kind of that amount of voltage is given to the LED, and the proportional amount of light is sent to the LEDs, and that's what we are able to see as colored images. So an alternate to this RGB is Y, CR, and CB, chrominance and luminance components. And if you see over here, RGB or the opposite, so yellow, CR, and CB, these are the colors that you can see in magenta, magenta, cyan, and yellow. These are the inverse colors. But then Y, CR, CB is something different. We will see their formula. Okay. So Y, CR, CB, these three planes. So what we do, we take 8x8 blocks from each of these images and perform its discrete cosine transform. We will talk about DCT in great detail today. And when you take its transform, it's obvious that you get an 8x8 block. Now what you do, you quantize this image. Okay, and how is the image and the quantized image? FQUB is actually what is sent over the network. And how do you quantize? So there is some quantization table. Okay, and this quantization table is actually guided by some coding tables. And you obtain the images using the zigzag scan. So the images have a header file. There are some tables and data. Okay, so actually this is the JPEG. This is how you are storing the JPEG file as. Not this FQUB, is the you store it as a JPEG file. So you have quantization tables, you have coding tables from the tables, and how do you code them? You do entropy coding using diffusion and RLC, run length coding. Okay, So first we do a discrete cosine transform of each 8 cross 8 pixel array shown over here. Then we quantize it using some table or using some constant. Then we actually use zigzag scan of this quantized image to exploit the redundancy. And what do we do? As I mentioned, the low frequency and high frequency. So in other words, you can say there's a DC component and there are AC components. So the AC components are actually encoded using the run length coding or RLC. Let me write that down. AC components are coded using RLC or run length coding, and DC components are coded using DPCM or differential pulse code modulation, which we had learnt in the previous week. Okay, and the final output is coded using entropy coding, let's say Huffman, which is the most efficient one. So what is an advantage of DCT? Why are you using DCT or not something like DFT? Okay, like we had talked about DFT, 1D DFT. So similarly for images we have 2D DFT. So let's take an example of what happened. Just a example 1D. So suppose you have some kind of a graph like this. Okay, so when I, let's say, take this 1D DFT, then I get some kind of a graph like this, let's suppose. And if I take a 1D DCT, I get some kind of a graph like this. So although these are imaginary pictures, but then I want to emphasize something. You see, this 1D DCT has decayed to 0 very early. Okay, so all 0, but you see over here a significant up to in the DFT coefficients, a significant portion is non-zero. Okay, so what do I do? Let's say I truncate some amount of this and some amount of this. Okay, now when I truncate this, I get something like this and something like this. Fine. Now let me reconstruct both of them back. Okay, I am assuming that I have truncated same number of samples. Okay, that's important. You are truncating, both of them are same endpoint DFT and endpoint DCT, and you are truncating same number of samples. When I reconstruct them, what will I observe? In case of DFT, what I'll observe is that there is some difference or a significant difference between what I had earlier and what I have now. But in case of the DCT, I will almost get the same image. So I have good deal of reconstruction error, which is high in DFT and low in DCT. So that's the advantage of DCT. You can compress, you can eliminate a lot of coefficients but still get the good chunk of data back. So actually, how do we perform our okay, Jagannath, can you just tell me if everything is clear, or in case anything?
Yes, sir, it's clear.
Okay, fine. So how do we perform 2D DCT? So basically, let's say you have a 3x3 array. Okay, so first we'll consider each row individually. Okay, this is a 3, this is, you can see these are linear arrays. Okay, this is 1, this is 2, this is 3. Each of them are individual sequences of their own, so I can individually perform their 1D DCT. Okay, 1D DCT. and you can do the same over here. As a result, you'll get modified, you'll get the corresponding 1D DCT outputs. Similarly, now what I do, now I choose each of the columns. Okay, they are also separate sequences, 1, 2, 3. Okay, I also do their 1D DCT, and then I get their corresponding output. Okay. So first what you have done, first you have done row wise DCT, then you have done column wise DCT, and each of them was 1D. Okay, and for a this left cornermost is called the F00 or the DC component of your image. Okay, and the rest all of them are your high, I shouldn't say high, I should say these are your AC components. And then why do we go for quantization? And that is because we want to reduce the number of bits per sample, so that we use lesser bandwidth and automatically we can adjust more users into our bandwidth. So we know the quantization formula FQUB, so you can do either round or truncate of f of u comma b and q of u comma b. Okay, and I need to inform all of you one more important thing, which is that we are in week 11. Okay, so we have week 12 left, and that will be, in that I will be solving the this semester's assignments that have been provided. Okay, so I'll be solving this runs assignments. Okay, not all of them, some of them, and in case you have doubt we may have a discussion. Okay, and that's on 16th, right? And we will also have another session, and this is a 2-hour session. Okay, the 2-hour session, and on 20th of October, okay, we will have a 1-hour complete revision session. Okay, I will try to, in a very fast way, I will try to revise all that has been covered in these 12 weeks, I mean actually 11 weeks. Okay, so in the time, and 20th October is Friday, and the time is 8 to 9 p.m. This will be a 1-hour session only. Okay, so I hope that's clear to everyone. Is that fine?
Yes, sir.
Okay, and when is your exam?
Suppose it's on 28.
2/8, right?
28, yes.
Okay. So okay, so for example, let's say 101101, which is equal to 45. You see, intentionally what have I done over here? You might be thinking that the MSB is 1, shouldn't this be a negative number? Actually we are dealing with images, and images have the intensity levels as unsigned numbers. So here we are using unsigned integer representation, so that's why its MSB will not be a signed bit. So when I want to truncate it to 4 bits, what do I do? 45 by, so when you want to make it 4 bits, how many bits do I remove? 2 bits, right? So 2 to the power 2, and then we take the, we're talking about truncation, we're talking about floor, so we'll get 11, and that's 1011, and that's obviously what you get. So when you have 101101 and you remove 2 bits, that's what you get. Okay, so higher the bit truncation, significant loss of precision, and this quantization is the source of error in lossy compression. Okay, this is where our data gets lost, that's why it's called lossy. And then the quantization can be of two types. One is uniform, and what do you mean by uniform? This number q over here, this q of u comma v is constant. So you see over here there's a difference. Q is a function of u and v. U and v are the coordinates of our transform domain, u and v. Okay, so this is the 2D DCT transform representation of our image. Okay, and then if it's uniform, then you can surely have a non-uniform variant, in which what do you have? Actually your eyes are more sensitive to low frequencies, and over here low frequencies are concentrated in the upper left corner. Okay, so these bottom right corners are high frequencies, and that's where you can do fun. So what you can do, you can have custom quantization at various places, and the tables are put in image header, the header that I had shown you over here. This header, you can put the tables over here, and JPEG defines two default quantization tables for luminance, which is the Y component, and chrominance, which is the CRCB component. Fine. So now let's briefly recap Huffman encoding. So suppose I have taken some signal and statistics of the image. Okay, by statistics I mean you have the, what is an image? Image is a matrix of integers, and I take some histogram of the integers present, and then I see that the pixel values, say 18, 25, 255, 128, 200 and 140. The others are negligible, and their relative frequency. Okay, you have a histogram, so you can obtain the relative frequency, and that relative frequency is nothing but a probability. So you see, obtain the corresponding probabilities: 0.6, 0.3, 0.06, 0.02, 0.01, 0.01. Okay, so correspondingly, if we may have some binary codes for them by default, and these are 8 bits in length. So 0001, 0010, and so on and so forth. You will have all 8 bits. Okay, all 8 bits. So your average length directly, if you try to send them, it will be all 8 bits. But then if you do half-man coding, okay, if you do half-man coding, this is 0.6, so this will have highest probability, so you can represent it by single bit. Then comes 0.3, so you use 1, then you go further down, slower, so you keep on increasing the number of bits. And over here the two probabilities are the same, so I replace this one by 0, 0 by 1. So here you see I represent this by 1 bit, 2 bit, 3 bit, 4 bit, 5 bit, 5 bit. And then what is my average bit length? This is my px into x, so it's 0.6 times 1 plus 0.3 length of x times 2, so on till 0.01 times 5. And what do I get? I get 1.56 bits per intensity level. So isn't, if I do half-man coding for the DCT coefficients, isn't that really good? I save from 8 bits to 1.56 bits. I get more than 4 times data compression. Okay, so that's the half entropy encode, half-man encoding that I was talking about, that we do in the last stage over here. Okay, now we talk about zigzag scan. Okay, so as I had mentioned earlier, your low frequency components over here, these are your edges, these are your vertical edges, these are your horizontal edges, and these are high frequency components. Fine. So as you move diagonally downwards, you will be able to get at higher and higher coefficients. So a good way to actually obtain these, at the end of the day, you have to these are a matrix and you have to send them in a bit stream, in a linear way, okay, in a single line. So the way in which we actually send the data is like this. We start from the lowermost pixel, we go right, then go down, then go down, then go over here. Okay, so we follow some kind of a pattern like this. Okay, are you able to follow with me what is going on over here?
Yes, sir.
So Jagannath, what kind of a pattern is this?
Zigzag,
Zigzag, absolutely.
diagonal.
So you see, I'm not directly going from low to high, I'm collecting all the lows and then I'm slowly and gradually going to higher ones. Okay, so based on these patterns, I mean, now let me give you an example to make this clear. So let's say I have 9 6 3 6 4 2 3 2 1. So first I collect 9, then I collect 6, then I go over here 6, then I go over here 3, then 4 3, then 2, then 2, then 1. Okay, so high frequency, low frequencies over here and high frequencies over here. Okay, so in that way you have actually clearly arranged your pixels from low frequency to high frequency. Okay, and the first entry is your DC component. Okay, so you have mapped a 8x8 matrix, because you are taking an 8x8 sub block from each 8x8 pixel sub block from each image, and then you convert into 1x64 vector. Now when you have each of these vectors, okay, so you have, let's say, a big image, and from this image you have this 8x8 block, you have this 8x8 block, you have this 8x8 block, and several other blocks. Okay, you are transmitting this block as a 64 bit vector, then you are sending this block then you're sending this block. Okay, so each of these blocks have a DC component at the beginning. Okay, and then you're obviously you have to send and they occupy some certain number of bits. So what do we do with the DC component is that we encode them using DPCM. So what happens in DPCM? In a DPCM, let's say the first entry is 45, the first block has a DC 45, second block has DC 30, let's say 32, let's say 36. Okay, so first one we send as it is, the second one we encode the difference. Okay, so 30 minus 45 is minus 15, 32 minus 30 is how much? 2. Then you have 36 and you are to send 4. Okay, so that rather than sending all these big numbers, you are sending small numbers, so automatically you are reducing the bit requirement. Okay, so that's the how you encode the DC components. And then for the AC components, we do something called the RLE, or run length encoding. So what happens is that, as I mentioned, this 1 cross 64 vector that I had shown above, that is to say they have lot of zeros, and that happens especially towards the end. Why? Because images tend to have very less high frequency components, so when you are sorting them out, you see the last few elements will be very small compared to 0, and we have also quantized them. Okay, so the quantization is very important. So once we are quantizing, you will be able to see even more zeros. So when you have lots of zeros, okay, let's say 25 such zeros, would you be sending 25 into 8 bits, or even 25 into, and how should you send? I mean, you also have to show that there are 25 0 bits, right? So what do? We encode the series of zeros as a pair. How do we pair? The pair will be skip comma value. And what is skip? Skip is the number of zeros and value is the next non-zero component. Okay, so let's say 1 2 3 4 5 1 1 1 2 3 4 5 6 7 2, so on. So these 5 bits are being sent as skip how many. So the when it will decoder will read this, it will say that I have to skip 5 places because there are 5 zeros, and the next value will be 1. And then this one, there are 7 zeros, so you skip 7 zeros and the next value is 2. And let's suppose I am in a place where, let's say after 2 I have all of them are zeros till the end. Okay, so in that case what do? I simply send 0, and this 0 will actually, I'll send actually 0 comma 0. So this 0 comma 0 is a special character which marks the end of block. Okay, so automatically you can understand, let's say I have given you 32 bits, and after that I get a 0 comma 0, which means that I have all of them are 0 till the end, so I have reached the end of the block. Okay, so this is called the run length encoding, and that's done for the AC components. And then okay, and then we talked about entropy coding. So how do we do entropy coding for the DC components? So you see there are actually multiple coding steps taking place. You first have the DPCM for the DC components, RLE for the AC components, and then you once again do entropy coding. So you're squeezing out as much information as possible and removing out all redundancies, and that's also the basis of how this live stream Google Meet is going on. So DC components are differentially encoded as size comma value, and then there is some table. You can refer to the slides or the notes provided for the table size value code. So if say the size is 0, that means 0 bits, you have value 0, the only value that can you send is 0, and there is no code for this. When you have to send 1 bit, what are the possible values? -1 and 1. So the code for -1 is 0 and the code for 1 is 1. When you have 2 bits, what are things you can send? -3, -2, 2, 3. So for -3 you have 0, 0, -2 have 0, 1, 2 you have 1, 0, 3 you have 1, 1. Okay, this is not the conventional coding, this is a different kind of a coding. Okay, so on. So actually these are the tables corresponding to JPEG. Okay, so there's no such fixed rule or fixed fixed rule in the sense there's no such mathematics behind why I'm choosing this, why I'm not choosing this. You could have chosen some other coding scheme as well, but this is JPEG, it's a standard, and every standard has some fixed rules which have to be obeyed both by the transmitter and receiver, so that you send and receive images properly without any error. Okay. For example, let's say I have a TC component which is 40 and previous one was 48. So what's the difference? The difference is 48, 40 minus 48, and that's -8. And for -8 you would require size 4, and you have size 4, the code corresponding to that is 101. Okay, and the value is actually -8, and the code corresponding to that with size 4 is 0111. Okay, so what we actually send is size and then value. You end up sending 101 0111. This is what you send instead of sending 40 directly. And then you have to also do entropy coding of AC components, and the AC components range from -1023 and 1023, and this is also coded as S1 S2 pairs, where S1 is run length or size, where run length is the number of consecutive zeros, and size, and what is the size? Size is the number of bits required to encode next non-zero AC component, and this size ranges from 0 to 10. Actually don't represent 10, we represent it by A. And then S1 is actually Huffman encoded. Okay, and then S2 is the value is the value of the AC component. So what am I trying to say? You see, a few minutes back I had told you, where was it, we had skip and then value, right? So in skip we are trying to first note that we are first trying to encode skip and then the value. We encode the value as first size of the value and then the actual value. Okay, and similarly we have another table for AC. I am not showing the table, that's a very big table. And so based on that I am showing you an example table. Let's say a matrix 40, 12, 1, 4, 1, 2, 3, 4. Then 10, minus 7, minus 4, rest all are 0, 1. Okay, so all zeros. So this will also be all yeah, 8 cross 8 matrix of the image. So oh sorry, so what will you do? We have to first do zigzag scan. Okay, and then from here it's all zeros. Forty, 12, 10, 1, minus 7, 0, 0, minus 4 and all zeros. Okay, I think I have to check the settings. Oh, now I got it. Okay, so this is the DC. I am ignoring the DC for now. For the AC, first how do I denote this 12? 12 is 0 zeros and its coding is 0412 1011 1100. So this is the code for 0, 4 related to size and value. Okay, sorry, run length, what was it? Yeah, run length comma size, number of zeros, that was 0, and size for the next non-zero. What is the next non-zero? That's 12, and 12 will require 4, size 4, and this one is the code for 12. Similarly 10 will be 0, 4, 10, and that's 1011 1010 1 0 1 1 0 0 1 minus 7 0, 3 and 7 1 0 0 1 2 3, and then we have 2 zeros followed by a 4. So what is the coding? We have 2 zeros, run length is 2, and next non-zero is 4, which has a size 3, and that's 4. So how do you write? 1 1 1, how many ones? 1 2 3 4 5 6 4 5 6 0 1 1 1. That's the code for 2, 3, and then 0 1 1. That's the code for minus 4. And 56 zeros are there in the 00, 1010, then rest all bits are 0. So I've shown how you encode the all of them by zeros. All the AC components are encoded. Okay, so is this clear? Okay, and where are the common applications? So you use it in JPEG format, and you also use it MPEG 1 and 2, which is the standard corresponding to videos. Okay, you also use it in MP3, advanced audio coding, WMA. I don't know how, but then that's what the slides have mentioned. Maybe some simpler version of this is actually used. And what is most important is that all share in some form or another a DCT method for compression. Okay, and now let's move to JPEG. Okay, through JPEG. So JPEG has actually 5 modes. So the first mode is sequential mode, and what happens in sequential mode, each image is encoded in single left to right and top to down. Okay, single left, right and top to down bottom scan. Okay, and the technique that we have been discussing so far is an example of such a mode, and is also called the baseline sequential mode, and it supports only 8-bit images. Okay, then there is something called lossless mode, and there's really loss involved in it because there's good quantization. And what it does is that it does some kind of a predictive lossless, I mean there's no loss in it. Okay, and unlike the sequential which had quantization, here we don't have any quantization. We do something called predictive coding, and this is also based on DCT and quant. So you have an image, and you actually have some kind of a prediction of this image, and this prediction of the image minus the image, there is some kind of loss, and that loss is encoded using the Huffman encoder. Okay, and this is why you called it lossless encoding, because you are encoding and directly sending out the error. And what happens in a lossless mode? So suppose let us consider certain pixels C, B, A, X, okay. So you go around like this and go downwards. Okay, so we actually predict each pixel beforehand based on the earlier pixels. So for example, I have shown a pixel X over here, and we try to predict x. Okay, and how do you predict? There's a predictor, there's a prediction corresponding to x. Predictor p1 is a. Okay, so these are the things that I've already been encountered earlier. P2 is b, p3 is c, p4 is a plus b minus c, p5 is a plus b minus c upon 2, p6 is b plus a minus c upon 2, p7 is a plus b upon 2. Okay, and then for first pixel, which is the 0, 0, we have to use the exact value at that point, and then the first row will always use the predictor p1. And what does p1 mean? P1 means the pixel earlier to the left of it. First column will use p2, and what is p2 means? B, and b is the pixel just above it. And for rest we use best of the 7 that have been mentioned over here. Okay, and then we actually have the prediction and the actual, so we take the difference and then we send the difference out. Okay, so it's very similar to all the encoding and all that we have done. We are sending the encoding differential, we are doing differential PCM, we are sending the difference and not the actual one. So once you send the first pixel and the differences, you can automatically get back the actual image, because you have these predictions, and based on the prediction you can do linear algebra and get it back. And then there is something called the progressive mode. So what happens in progressive mode? In progressive mode, it allows a coarse version of an image to be transmitted at a lower rate, and then it is progressively improved over subsequent transmissions. First we send the DC component and the first few AC components, and then we gradually send more and more AC components. It's like sending a broad coarse image and then a rough image or some low resolution image, and then slowly increasing the resolution. And then there is successive approximation, which all the DCT components are sent few bits at a time. For example, first we say 4 bits are sent starting with MSB of all pixels in its first scan, and then we send in the second scan the 5th bit of the all the pixels, and so on. Okay, so progressively things are sent, not all together. You're not sending all the pixels together. And then we have something called the hierarchical mode, and it is used to support multiple resolutions of the same image, because it can be sent on various displays. For example, you may be viewing the image on a tablet, you may be viewing the image on a laptop, your television, your mobile phone. Okay, and there's a 3-level hierarchical encoder decoder, and let me draw its image. Let's start from below. You have the image I, first you do 2x2 downsampling, you get I2 bar, and then a 4x4 downsampling, and then this is encoded, decoded, and then you have 2x2 upsampling. And then you subtract that from the original 2x2 upsampling, and then in every case you see you're encoding the differences and not the images directly. That's the main motive. Encode, decode, and then you do a 2x2 upsampling over here, and you again take the difference from the original image, you encode that. Once you encode that, I form a boundary level 4, level 2, level 1. So this entire left side is the encoding, where actually I have taken the big image and then I have subsampled it into smaller halves, and then you're sending the subsample errors. Okay, you're saying, see, I'm taking the difference and sending the errors, and then but decode block, I have 4x4 upsampling over here, I4 bar, then I do a 2x2 upsampling. Now I add it with this 2x2 level, get I2 bar, I again upsample this, and I get the reconstructed image back, and this module on the right is the decoder unit. Fine. So that was all about your hierarchical JPEG, and we have completed our module on JPEG. Okay, now we will talk about DCT. So first we have one-dimensional DCT, and we define the DCT as an DCT matrix. First let me write the full form: discrete cosine transform, and it's an enclosing matrix which has the I, jth element as Cij is Ai cos I 2j plus 1 pi times 2n. N minus 1. Okay, and note that this C is an orthogonal matrix. And what do you mean by orthogonal matrix? C transpose C is I, correspondingly the inverse of the matrix is its transpose itself, and this transposition actually helps you in solving matrix equations like a y equal to c x c transpose. So you want to write x in terms of y. So what do? First you try to remove c from the left hand side, so multiply both sides, left hand side by c inverse c x c t. This is I, and c inverse is c transpose, so c transpose y equal to x c transpose, and C transpose is C inverse. So what can I write? C transpose y x C inverse. So you multiply the right side by C so that you cancel the C inverse on the right hand side. So you get x into C inverse C, and that's x. So you see how orthogonality helped us in getting back this. We'll show the use of this expression later. and this DCT matrix is a real orthogonal matrix, and let me write it for an encrossing matrix. The square root of 2 upon n 1 upon root 2 cos pi upon 2n till cos n minus 1 pi upon 2n by root 2 cos 3 pi upon 2n cos 3n minus 1 pi upon 2n root 2 cos 2n minus 1 pi upon 2n cos n minus 1 2n minus 1 pi upon 2n. Okay, this is your DCT matrix, and you can correspondingly find the C inverse by taking the transpose. Okay, so the transpose, you just interchange the rows and columns. And then if you look at the DCT algorithm, there are two ways you can do it. One is the direct 2D method, where you apply the 2D transform, whether it is DCT or DIDCT, directly on the n cross n image, or the alternate row column method. And what is this row column method? You remember long back where is this? Yeah, I talked about how to perform DCTs separately. So first you take rows, they are individually 1D DCTs, and then you take the columns, and then you take the 1D DCTs. So that's row and column one at a time. That's what I call the row column DCT. Okay, so it requires 2n instances of 1 point, sorry, it's not a 1 point, it's instances of n point 1D DCT. Okay, so by the way, just wanted to know, have any one of you done any image processing course? Saranya or Jagannath? Okay, so maybe I think if you do over here, you Saranya, you have done, right? So are these concepts covered in DCT and all that I have taught, JPEG? Have they been taught in these in the courses? I would like to know, because actually I do not work in this image processing domain, so I'm not sure about the level of things that I should be covering over here. So whatever I've taught over here, have you learned that already in image processing? So have you covered these topics like JPEG and DCT, all of them? Okay, Jagannath, you said you have not covered these things, so I'm continuing you for that. Otherwise it will be quite redundant if I repeat it for everyone who knows over here. Okay, so an important thing over here is that in a 1D DCT, you actually require the direct implementation requires n square multiplications and n times n minus 1 additions for an endpoint. And for a 2D DCT, you require how much? N to the power 4 multiplications and n cube times n minus 1 adds. Okay, so one important thing is that this method is quite, despite the fact that there's a lot of computations, these matrix transformations on all of these lead to a very uniform or structured processing architecture. Okay, and when you talk about fast algorithms, the fast implementations, the 1D version will have order of n log n complexity, and for 2D you will have order of n square log n. Okay. And so we have been talking about image compression till now, and what we are saying is that for 3D, so you're saying for 3D algorithms, so we don't really where do you use 3D, can you please tell me? For example, in videos we do it frame by frame, so even if you talk about videos, so you take each image at a time. Okay, we don't process all of them together. And if you are thinking of new convolutional neural networks, then that's a completely separate issue. You do them in parallel. Okay, it's not that you do one by one, you do them in parallel. The obviously the number of multiplications increase over there, but then it's not that it's something different. I mean, if you're talking signal process, normal signal processing, there's nothing as such called 3D. Suddenly, did you ever encounter 3D algorithms? I mean, I don't have any idea. I may be may not be not so knowledgeable about this. Can you please confirm? I have not encountered 3D, and I know of things that often if you have something in 3D, then you convert that into 2D using certain transformations that there in Keshav Kepari's book. And moreover, if you talk about 3D for the multiple loops, okay, 3D assignment. Okay, so if it's an assignment, then I think you need to figure it out yourself because it's an assignment, unfortunately. So maybe you can check out the hint that I've shown over here. Yeah, it might be possible. Maybe 3D when it's being talked about, so it might be convolutional neural networks as well. Bunch of images given together. Okay, so coming back to our plain old DCT, classical image processing, not deep learning. So DCT image, we take the most important coefficients that we want to preserve are located in the upper left corner. The semi important ones are in the intermediate zone, and the least important ones that you can kill are in the bottom right corner. Okay, so and this is based on our human visual system, in which the importance is based on how much our eyes can tolerate. Okay, if you play with these, then the image is gonna be destroyed. This one will have some effect. Okay, so maybe we may not be able to see the background clear, or some part of my face a bit distorted. Okay, but the distortion may not be so bad. And the least important ones is even if you make them all 0, nothing is going to change. Okay, so if you actually look at the DCT 2D DCT, we can actually visualize it as C X C transpose, where C is our where you are applying the transforms one after the another, and when you do the inversion, you actually get the X C transpose Y C. Okay, so what do you write mathematically for inverse DCT or IDCT? Let's suppose X is our input image, Xij, matrix of n square numbers, or output YKL 2D DCT of X, A naught is 1 upon root 2 for k equal to 0, and k is 1 for k not equal to 0. Then the reconstructed image with indices s and t, we obtain it as summation over k equal to 0 to n minus 1, l equal to 0 to n minus 1, ykl ak al cosine k 2s plus 1 pi upon 2n cosine of l 2t plus 1 pi upon 2n. Okay, finally we will be able to see that Pn of I comma j will satisfy x of I comma j for 0 comma y j minus 1, which means that if you do inverse dct you will get back the same image. It's obvious. And there's something called linear quantization, and what happens in that, we use some kind of a quantization matrix QKL, is given by this expression. So the quantization matrix Q is 8, 16, 64, goes up to 64, goes up to 120. So P is called the loss parameter. And how do you obtain the quantization matrix? No, how do you obtain the resultant? So let's say you have a DCT matrix phi. So in order to obtain quantized value, you do y dot q. Now what do I mean by this dot? It means element wise division. So the first element 0 comma 0 is divided by 8p, 0 1 comma 0 is divided by 16p, and so on. Okay, and higher the value of p, so the denominator in the quantization is more, and that means that you have more loss, and that's why it's called the loss parameter. And let's say that depending on the value of p and how much bits per pixel you have, so when you don't have anything, so you have 8 bits per pixel. When you have p equal to 1, you have 3.89 bits per pixel. For 2 you have 2.98, for 3 you have 2.30. okay, so you are compressing the image more and more. And so whatever we have learnt about JPEG images, where black and white, you can easily extend it to color images or RGB images. Okay, so the baseline JPEG, what does it do? It defines the luminance coordinate y as 0.299, 0.587, 0.114 times RGB. okay, yes, a linear combination. And then you define other coordinates u b minus y and v as r minus y. So now we have converted RGB into YUV, and you apply DCT independently to Y, U and V using the Q matrix. Okay, and an important thing is that human eye is more sensitive to Y. So what you can do, you can compress U V much more, and as a result colored images are even more compressible than black and white images. Okay, and when you want to reconstruct back after doing all these compression and shredding, you get back your blue, red and green. By this formula. And in fact, when I said that Y is more sensitive and U, V are less sensitive, you can do something called chroma. These are chrominance values. So chroma subsampling. So what does it do? Averages CB and CR values to save space. So for example, I can say take a 2x2 block for a RGB image, so they have their corresponding Y, CR, CB components. So I don't subsample Y because Y is a very sensitive parameter, and this equivalent block CB and CR, all the four, actually it's a 4x4, but then they have the same value. This is called 2x2 chroma sampling, and this is what is used in most of our webcams. Okay, and then I actually should mention the DCT formula. X of k equals to E of k summation n equal to 0 to n minus 1 x of n cosine 2n plus 1 pi k upon 2n, and the IDCT is xn equal to 2 upon n and k equal to 0 to n minus 1 ek x of k cos of 2n plus 1 pi k upon 2n, n ranging to these values. ek is 1 upon root 2, k equal to 0 and 1 when k is not equal to 0. This is your main DCT equation. It's very similar to DFT, but the biggest advantage is that you don't have complex numbers to deal with. It's simple real numbers. Okay, so for a let's talk about a 4-point DCT matrix. So the 4-point DCT matrix has the following representation: 1 by root 2, c pi by 8, c pi by 4, c 3 pi by 8, 1 by root 2. Actually this is after a lot of simplification you will get this, it's not directly, minus c pi by 4. C is actually cos c pi by 8, 1 by root 2, c 3 pi by 8 minus c pi by 4, c pi by 8 by 8, c pi by 4 by 8, 1 by root 2, x0, x1, x2 and x3. Okay, so you see there only n minus 1 equal to 3 true coefficients. Let me write it down as c1 hat, c2 hat and c3 hat, where c1 hat is c pi by 8 or cos pi by 8, c2 hat is c pi by 4 which is 1 upon root 2, and c3 hat is c 3 pi by 8. Okay, so now I shall move into the architecture. So I can write x0 as sum p0 plus p1 times c2 hat, x1 as c, it's all 1 by root 2, that's cos pi by 4. X1 is m0 c1 hat plus m1 c3 hat, x2 is p0 minus p1 times c2 hat, x3 is m0 c3 hat minus m1 c1 hat, p0 is x0 plus x3, p1 is x1 plus x2, p0 is x0 minus x3, m1 is x1 minus x2. And if I try to combine all of these in some kind of a structure which we already know as the butterfly structure in DFT, let me do that for the DCT directly. There are plus minus x0 x3 x1. Okay, this is the first butterfly. C3 hat, C3 hat, C2 hat, so I guess if I have studied properly, if I have studied the DFT or the DFT structures properly, can very well correlate how similar they look. Okay, and the best part of it is that they don't have complex multipliers, and when you have complex multiplier, there are alternate multiple multiplications involved in this. Okay, so we just have some more matrix multiplication simplifications, but that's with an 8 cross 8 matrix, so I'm not continuing further. So do any one of you have doubts? Sharanya, Jagannath, anything else you want to add? Your any questions, any suggestions? Because this is our last theory class. In next class we'll have revision. We'll be solving some questions. Okay, no issues. Okay then, so I am closing for today. Good night.